Good morning, everyone. Let me make a brief announcement in Japanese first. おはようございます。今日は望月先生が来られませんから、僕は一人で授業をします。僕の授業は全体日本語で教えることはできないと思いますから、英語で行いますが、英語が行いますが、授業の後はYouTube にアップロードしますから何かわからないことがあれば、YouTube で日本語の通訳してもらってください。あの、今日、今日と来週は、望月先生が来られない、2つの授業ですけど、この2つは多分一番数学的に難しい授業と思いますから、本当にわからないことがあれば、あのそのGoogle の、YouTube の通訳してもらってください。Um, as I just said in Japanese, I will be lecturing alone this week and next week because Mochizuki Sensei is unable to join us this week or next week. This week and next week are perhaps the most mathematically intensive classes of this semester. Maybe this week, next week, and the week after. So if there is anything that you have difficulty understanding in today's lecture, please go to the YouTube channel after this lecture and have YouTube translate the lecture for you. I will upload the transcript. I will upload the transcript, and then YouTube can also transcribe it for you and translate it for you. So please take a look at those transcripts and those translations in case there is anything that you have difficulty understanding in today's lecture or in next week's lecture. So last week, as you remember, last week we discussed speech production. Let me just go to briefly remind you of last week's lecture. Last week, we really started talking about speech. We talked about the voice source, how the voice box down here closes 100 or 200 times every second, and that closure causes a pulse, and that pulse excites the vocal tract. It excites the resonances of the vocal tract. And especially these first four resonances are important. The frequencies of these first four resonances determine what vowel you hear. And the periodicity of the pitch pulse determines what the pitch is of the tone that you hear. And so last week we synthesized A, E, U, A, and O, these five vowels, synthetically using an artificial glottis at 100 cycles per second and an artificial first, second, third, and fourth formant frequencies resonating. This week, I want to talk in much more detail about the analysis of different frequencies. This week, next week, and the week after. So this week, I'll talk about finding the frequencies. Next week, I'll talk about synthesizing speech in a new method using only the frequency information. And then the week after next, I'll talk about analyzing natural speech using the Fourier transform. This week, I want to define for you this concept called the Fourier transform. This is a very famous concept. If you go to Wikipedia, for example, and look up Fourier transform, you'll find many, many articles about the Fourier transform. It's a very important technique in all kinds of signal analysis, not just speech signals, but any kind of audio signal, any other kind of signal. And I want to introduce to you the reason that the Fourier transform exists. The reason that it exists is this concept called the orthogonality principle. If I go to Wikipedia, let's look up orthogonality. Orthogonality means right angles. A and B, the line segment AB and the line segment BC are orthogonal to each other. In English, orthogonality is the generalization of the geometric idea of perpendicularity. Perpendicularity means that two lines are perpendicular to each other. Orthogonal is basically a synonym for perpendicular. In English, those two words mean essentially the same thing. So as shown here, these two lines are perpendicular to each other or are orthogonal to each other. Those are two words in English that mean essentially the same thing. And the reason that we use the idea of orthogonality is that when you look up the dot product, we have this idea of a dot product between two vectors. The dot product between two vectors, as we discussed 2 weeks ago, if you take the dot product between the vector A and the vector B, that means you add up over all of their coefficients, A sub I times B sub I. And if you the property of orthogonal vectors is that if you take their dot product, the dot product is 0. So let's see if we go back to orthogonal and if we look up orthogonal vectors, then the key property of orthogonal vectors is that their dot product is 0. This doesn't mention that the dot product is 0. Okay, the key property of orthogonal vectors is that their dot product is 0. And the general orthogonality principle is when you take two signals and multiply them together, the product has an average value of 0. We will use that will be the key mathematical principle that we're going to use. That key mathematical principle will be applied to the analysis of musical chords like A major chord or A minor chord, different musical chords like you might play on a guitar or a piano. And I will use that as a special test case that we can use in order to test our understanding of the Fourier transform. I'll derive the Fourier transform in 2 steps. First, I'll talk about what's called the discrete cosine transform, which is like the Fourier transform, but not quite general enough. And then I'll generalize it to the discrete Fourier transform, which is a complex valued version of the discrete cosine transform. So let me get started. Let me describe those basic concepts. First of all, the orthogonality principle. Two functions are said to be orthogonal to one another if the average value of the product of those two pure tones of those two different functions is 0. So in particular for signals, the average value of the product of two pure tones with different frequencies is 0. If I take the pure tone cosine of 2 pi k little n over capital N, multiplied times the cosine of 2 pi m little n over capital N, where k is not equal to m, right? Then if I multiply them together and then take the average value is 0. So we can demonstrate that. So here's the cosine of 2 pi times kn over 20, where k is 3. Here's the cosine of 2 pi m times n over 20, where m is 4. So we have 3 complete periods, 1, 2, 3. We have 4 complete periods, 1, 2, 3, 4. If I multiply them together, I get this very complicated looking thing, but this very complicated thing has an average value of 0. If you look at it, you can almost see it. This sample is the negative of this sample. This sample is the negative of this sample. This sample is the negative of this sample, and so on. These samples come in pairs, 1 plus and 1 minus, and so that the average value is 0.0, right? So that's kind of an interesting fact in its own right. If you multiply together this fact, right? If you multiply together two tones at two different frequencies, the average value of their product is 0. That property is useful because it has one exception. There's one time when that doesn't hold true. That one exception is when k is equal to m. If you multiply together two tones at the same frequency, then the average value of their product is not 0, because that signal x of n multiplied by itself is x squared of n, and x squared of n is always positive. So if I create, if I set k is equal to 3, and then I create two different signals. One is if I set k is equal to 3 and m is equal to 3, if I set x is equal to the 2 pi kn over capital N, y is equal to 2 pi mn over capital N, now they're exactly the same signal. And so if I multiply them together, I just get x squared. And the average value of a cosine squared is 1/2. So let me run this code. I get x of n has 3 complete periods. Y of n has 3 complete periods. And so their product is actually cosine squared. And you can see that it varies from between 1 and 0. The average value of cosine squared is exactly 1/2. And so if there are 20 samples, the average value is 1/2 of 20, which is 10. So if the general statement of the orthogonality principle is that if I take the cosine of a tone at one frequency and the cosine of a tone at a different frequency, if I multiply them together and add up their samples, the sum is equal to 0 if they're at different frequencies. But if they're at the same frequency, then the sum is equal to 1/2 of the number of samples. So here's the general mathematical principle. This is called the orthogonality principle in English. And it's this general principle that when you multiply together two cosines, they're either equal to 1/2 on average if they're at the same frequency, or they're equal to 0 on average if they're at different frequencies. This is the key principle on which the Fourier transform is based. And this is useful, for example, for the analysis of musical chords. A musical chord is a combination of pure tones that sound good together. So we have two classical chord types that are taught when you learn how to play guitar or when you learn how to play piano. There's the major chord and the minor chord. A major chord is the root tone, and then a major third, and then a major fifth. The major third is 4 semitones above the root. So if the root tone is cosine omega naught n, then the major third is cosine of g to the 4th times omega naught n. The major fifth is 7 semitones above the root, so it's cosine of g to the 7th times omega naught n, where g is 2 raised to the 1/12th power, right? That's the multiplier for 1 semitone. A minor chord is exactly the same, except the third tone is a minor third rather than a major third. And the minor third is only raised by 3 semitones instead of by 4 semitones. Right, so we have g to the third rather than g to the 4th. So we can do an example with A major and A minor. A has a root frequency of 440 cycles per second, which is 2 pi times 440 over fs radians per sample. So if I run this code, I generate a major chord, which is the cosine of omega naught times n, plus the cosine of g to the 4th, here's g to the 4th, times omega naught times n, plus the cosine of g to the 7th, here's g to the 7th, times omega naught times n. And if I run this code, I can play the major chord. Can you all hear that? I think that that's audible to you. So you can hear that it sounds like a major chord. It sounds like 3 tones being played together, and those 3 tones sound harmonious. And in Western music, that's considered a happy sound, like the beginning of springtime. A minor chord in Western music is considered to sound more sad. So we take the cosine of omega naught times n plus the cosine of g cubed times omega naught times n plus the cosine of g raised to the 7th power times omega naught times n. Notice the only difference is the major third uses g to the 1/4 g to the 4th power, G raised to the fourth power. The minor chord uses G raised to the third power. So 4 semitones or 3 semitones. And if I play this, in Western music, this is considered to be a more sad sound or melancholy or thoughtful. So here we have a more happy or active sound, and here a more sad or thoughtful sound. Today, we're not going to do any more about music theory. Today, we're going to ask, if you were given one of these sounds, suppose you have a recording that you've, a musical piece that you've downloaded from the internet somewhere, and you want to find out what chord is being played. In order to find out what chord is being played, you want to try to analyze it. You want to try to take that signal and plot it. So let me just plot that minor chord. I'll choose 1/20th of a second. So fs is the number of samples in 1 second. I'll take 1/20th of that total. So I get fs over 20. And then I'll just plot that many samples. And I have, well, look at that. It's obviously something that has some pure tones in it. It's obviously not a simple cosine. It's quite a complicated sound, actually. It's not really obvious how to interpret this sound. It's very complicated looking. All right. What I'm going to propose in the rest of the lecture is that we can use the orthogonality principle in order to find a way to determine exactly which notes were being played. We can find exactly which frequencies existed inside that sound. And using our knowledge of those frequencies, we can determine exactly which chord was being played. Not just which chord, but we can tell exactly which notes were being played by the musician who played this chord. And I'm going to build that up piece by piece. I want to start out with something called the discrete cosine transform. The discrete cosine transform is exactly like the discrete Fourier transform, but easier. The idea of the discrete cosine transform is that we just use the orthogonality principle. We use our knowledge that when we multiply the cosine of at one frequency multiplied by the cosine at another frequency, that the summation of those samples is equal to 0 if they're at different frequencies. If they're at exactly the same frequency, or if k is equal to capital N minus m, that's a special case where basically k equals m means they're the same frequency. K equals n minus m means that they're at indistinguishable frequencies. In either of those two special cases, the summation of these samples is 1/2 the length of the summation. If there are capital N samples in the summation, then the summation is 1/2 of capital N. In the special case, when they're at exactly the same frequency. Otherwise, the sum is 0. We can do all of those summations all at once. Let me take every single possible cosine, capital X of 0 all the way up through capital X of n minus 1. Each of these rows will be, here it is. Oh, that's not useful. Each of these rows will be W of k comma n is the cosine of 2 pi times k times n over capital N. So the kth row is this cosine of 2 pi times k times n over capital N. This tone is the row of the matrix, right? So I take this tone and put it into the row of the matrix. That means if this vector contains cosine of 2 pi times m times n over capital N, this vector is this cosine. And so if this vector contains a frequency that's anything other than that row of the matrix, the average value will be 0. So anything that's in this vector that's at a frequency other than the frequency of that row of the matrix causes this element of the capital X vector to be 0. The only elements of the capital X vector that are not 0 are the elements of this vector where there's a row in the matrix such that K for this row in the matrix and M for the frequency in the pure tone in the sound that we're analyzing are the same frequency. So we'll get to see that most of the rows of these matrices will multiply by the signal and the result will be 0. The only results that will be non-zero will be 3 results, right? Those 3 results will be omega naught, g cubed times omega naught, and g to the 7th power times omega naught. Those 3 results will have non-zero products. Those 3 rows of the matrix will multiply times this vector in order to give elements in this vector that are non-zero. All of the other elements of the capital X vector will be 0. So we'll see that capital X of K will be n over 2 when K is equal to little m, the frequency in the X matrix, and 0 otherwise. So let me set that up. Capital N is 20. I'll just use 20 samples. Little m will be 4. I'll set X equal to a cosine that has 4 complete periods. So I'll set X equal to the cosine of 2 pi times little m times little n over capital N. And then I'll create my W matrix. W of K comma N will be the cosine of 2 pi times K times little n over capital N. And then by doing this matrix multiplication, right, I'm doing exactly this operation. Every element of the capital X vector will be one of these summations, where the summation will correspond to the kth row of the matrix. The kth element of this vector will be this summation at frequency number K. Right? And so when I can analyze that with my, I've created an X which has just this one frequency in it, and I plot the result, I find that the discrete cosine transform at frequency 0, it has 0 output. 1, 2, 3, and at frequency 4, it has a positive output. So I've just done this matrix multiplication between the W matrix and the X vector. And the X vector had just this one frequency in it. And so the result of this matrix multiplication has just one positive output at frequency number 4. It also has one positive output at frequency number 20 minus 4. So this is one kind of artifact. Frequency 20 minus 4 is indistinguishable from frequency number 4. Those two frequencies look the same. And so we can pay attention only to the first 10 frequencies and say of those first 10 frequencies, frequency number 4 is the only one that has a non-zero output. All right, so what we're going to do now is to use this kind of analysis and make it much, much bigger, right? Here we have only 20 different frequencies, but up here in the minor chord, I made this, how long did I make it? Oh, I made it 2 seconds long, right? So if Fs is 8,000, here, this is 16,000 samples. So now I have maybe as many as 16,000 different frequencies that I want to analyze, not just 20 different frequencies. All right, so let me go ahead and, okay, I'm just going to take the first 400 samples. Let me take the first 400 samples of the minor chord. So now I'll have 400 different frequencies. I'll choose 400 different frequencies. I'll create a W matrix where W of K comma N is cosine of 2 pi times K times N over capital N, right? And then I'll multiply that matrix W times the first 400 samples of the minor chord. And the result then looks something like this. I have 3 non-zero elements. These elements are basically 0. They're very small value. So I just have 3 non-zero elements corresponding to the 3 pure tones in that minor chord. Remember that minor chord had just these 3 tones in it. Omega naught, G cubed times omega naught, and G to the 7th times omega naught. For an A minor chord, I think that those are A C, and E. And that sounded like this. So there's a chord containing three tones, and here are those three tones. Here's the A, the C, and the E. And here are three other tones, 400 minus A, 400 minus C, and 400 minus E. Right, so it's kind of duplicated at both ends of the discrete cosine transform. Let's make sure that this is really the A note, 440 cycles per second. This is really the C note, and this is really the E note. We can zoom in on that part of the plot. Let me just set the X limits between 0 and 50 so that I can zoom in on that part of the plot. And I see that the first non-zero element is at element number 22. So frequency 22 has a chord. It has a pure tone. And 22, 3, 4, 5, 6, frequency number 26 has a pure tone. And then 7, 8, 9, 10, 11, 12, 13, frequency number 33 has a pure tone. So the three tones in this minor chord are frequency 22, 26, and 33. Notice that this frequency is that the third, the minor third is closer to the root tone than the major fifth. The major fifth is further away. So we have, oh, here I have 25. 1, 2, 0, 20, 21, 2, 3, 4, 5, 6. I think this should be 26. Yeah, so we have the three pure tones in this chord are at the 22nd frequency, the 26th frequency, and the 33rd frequency, right? Let's just verify that those are in fact the A and the C and the E. So we can, if omega is 2 pi f over fs, we can solve for little f in cycles per second. It should be little f is equal to omega times fs over 2 pi. Well, actually, omega is 2 pi times k over capital N. So we get that the frequency f is k over n divided by fs. So little k over capital N divided by f sub s. And so I can actually plot the, I can set the x label to frequency f in hertz. I can find the frequencies f, which are k times k over capital N times f sub s. And I can plot those frequencies as the x-axis and plot the y-axis as capital X. And I see that the frequency here of the first note is 440. And the frequency of the second note is 512. And the frequency of the third note is 660. So these are exactly the A and the C and the E of an A minor chord. All right, so 440 and 520 and 660, the minor third and the major fifth. So that's the key idea. That's how we can use the orthogonality principle to find out which pure tones exist in any particular signal, regardless of the signal. You can do this with arbitrary signals. You can do this with earthquakes. You can do this with images. You can do this with cloud patterns. You can take any signal that you want and analyze it, pretend that it's the sum of pure tones, and find out which pure tones are present. Now, there's only one complication. The discrete Fourier transform addresses this one complication. This one complication is sometimes those pure tones are sine waves instead of cosine waves. And so we need to deal with the possibility that the minor third is made out of sine waves instead of cosines. So let's try it. Let's set the root tone at 440 hertz. We'll set the sampling frequency to 8,000. We'll set omega naught is 2 pi f naught over fs. And then we'll create a sine minor chord, which is the sine of omega naught times n, plus the sine of g cubed times omega naught n, plus the sine of g to the 7th times omega naught n. And that sounds like this. In case you're wondering, here's what the cosine minor chord sounded like. That was the cosine. This is the sine. I don't know if you can hear any difference, but I can't hear any difference between those. To me, those sound exactly the same, right? So if those are exactly the same, we want to be able to pick out those three pure tones, even though they're made of sine waves. And the problem is that a W matrix composed of cosines, where W of k comma n is the cosine of 2 pi kn over capital N, fails. It's unable to find that. If I do the cosine analysis, I'll take the minor chord made out of cosines and multiply that by W. If I do the sine analysis, I'll take the minor chord made out of sines and multiply that times W. And what we find is that the cosines have very strong elements at all three tones. But the sine minor chord has almost nothing at the root tone. The element at 520 has a little bit of information, but not as much as it should. And the element at the major fifth has almost no information again. So just turning it from even though the cosine and the sine sound the same to a human being, the discrete cosine transform is unable to analyze them. The way that we solve that problem is by multiplying by cosines and sines at the same time. So let's take the sine wave. Instead of the cosine, we'll take the sine wave. The sine of 2 pi times k times little n over capital N. Let's multiply that by the cosine chord and multiply that by the sine chord. And now we're going to wind up with the opposite problem. The sine chord has very strong elements. So here we had the blue ones are good and the red ones are bad. Here we have the red ones are good and the blue ones are bad. The cosine minor chord is not analyzed well by sine waves, and the sine chord is analyzed just fine by sine waves, but not by cosines. So we know that if W is made of cosines, it can analyze cosines, but not sines. If W is made of sines, then it can analyze sines, but not cosines. And the way we do both at the same time is by using complex numbers. Complex numbers are the sum of a real part and an imaginary part. An imaginary part is just a real number multiplied by the square root of -1. We call these imaginary numbers because they don't exist in the real world. The real world doesn't have imaginary numbers. But they're a useful thing to have on our computer because on our computer we can use imaginary numbers to do two kinds of analysis at once, right? The computer can analyze cosines and at exactly the same time, it can analyze sine waves. So we imagine that these numbers exist. They don't exist in the real world, but we imagine that they exist because they allow us to do some kinds of analysis that we wouldn't otherwise do. Specifically, they allow us to simultaneously detect a minor chord made out of cosines and also simultaneously detect a minor chord made out of sines. So we do that by multiplying the matrix W times the vector X in order to get a vector capital X. The vector capital X, its kth element, will be n over 2 if x of n was the cosine of 2 pi k n over capital N. And it will be j times n over 2, a purely imaginary number, if x of n is the sine of 2 pi k times little n over capital N. Right? We don't really care whether the input was a cosine or a sine. The human ear can't tell the difference. To a human, cosine, sine, they sound the same. And so we don't really care whether it's n over 2 or j times n over 2. Those two things sound the same to a human being. And so we can force them to sound the same in our analysis by taking the absolute value of x of k, which is the square root of the real part squared plus the imaginary part squared. And you can do this using the NumPy absolute function. So here we can use j equals 0 plus 1j in NumPy, and then set n is equal to 400, and w will be this is important. We need to specify to NumPy that we're creating a complex valued matrix. If we don't tell NumPy that this has to be complex, then NumPy will not make it complex. It will be real valued, and so it won't be able to handle the complex numbers. And then we just set the knth element to be equal to the cosine of 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. So we're doing two kinds of analysis at once, doing the cosine analysis in the real world and doing the sine analysis in the imaginary world. We can take the cosine minor chord and find its Fourier transform, take the sine minor chord and find its Fourier transform. And if we plot those, let me plot NumPy absolute value of the cosines and NumPy absolute value of the sines in order to show you that those two absolute values are the same. Here are the absolute values, the cosines detected by the discrete Fourier transform, and here are the sine waves detected by the discrete Fourier transform. And you can see that in both cases, the Fourier transform has detected them. The cosines were detected as real numbers. The sines were detected as imaginary numbers. But since I plotted the absolute value, it doesn't matter whether it's real or imaginary. We get it regardless of whether it's real or imaginary. We've just done basically two different types of analysis at once, both the cosines and the sines. This kind of analysis is the basis for most of chemistry. It's the basis for most of physics. When people talk about detecting the light of the Big Bang at the beginning of the universe, they're usually talking about using the discrete Fourier transform to do it. It's definitely the basis of all types of audio analysis. It's the basis of a large degree of image analysis. Recently, I have a colleague in civil engineering who is using discrete Fourier transforms to analyze the drying of asphalt. When you pour asphalt on the road, you can use radar in order to detect how dry the asphalt is. And they're using the discrete Fourier transform to help them detect the drying of the asphalt. So it's widely used. This analysis that I've shown here, multiplying by this capital W matrix, creating this capital W matrix, and then doing a matrix multiplication is so important that NumPy has a separate function for it. NumPy's function for it is np.fft.fft. And if we take the FFT and then take the absolute value of the result, then you'll see that this produces exactly the same output. This output from NumPy FFT is exactly the same as this output. So this entire lecture that I've taught you today is really just teaching you how to, what is the mathematics behind this function, NumPy FFT FFT. Let's look it up actually. So here's the manual page for numpy.fft.fft. In all of the future homeworks after today, you'll use this operation to calculate the Fourier transform. But only for today's homework, I want you to go ahead and create your own capital W matrix in order to do your own Fourier transform. So this week's homework will be simply to create this capital W matrix, the cosine of 2 pi kn over capital N minus j times the sine. So if I import the homework and then look at it, and then if I type help homework 8 DFT matrix, you find that there's only one method. That one method has only one input. Capital N tells you how many columns should be in your matrix. And it has only one output. Its one output is just a DFT matrix that has to be a matrix of type D type is complex, and its knth element has to be the cosine of 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. You can test it using a simple cosine with an arbitrary phase. So if you feed in this simple cosine, this is a cosine with a phase other than, it's not a perfect cosine and it's not a perfect sine. It's halfway in between those two. If we do the Fourier transform of this x, we should get we should get a Fourier transform that has just one non-zero element at its element number 3, frequency number 3. When I run this code, of course, I get an error because I have not yet written the homework. So let me go ahead and open the homework and show you how to write the homework. Here's the homework, DFT matrix of n. So rather than the runtime error, I would like to create a W matrix, which has a size of n comma n, and it has to have a D type of complex. All right. And then once we have our n by n matrix, we want to, for k in the range between 0 and capital N, for n in the range between 0 and capital N, we want W of k comma n to equal the cosine of 2 times pi times k times n over capital N minus j, no, not 1 plus 1j, 0 plus 1j. Let's see, can I say 1j times the sine of 2 times pi times k times n over capital N. I'm not sure if this 1j will be enough in NumPy to tell it that I want the square root of minus 1. Let's find out if that works. We'll return W. And if I save that, and if my notation has worked here, if 1j is sufficient to create j times the sine, then that should give us a successful result. Let me try running this again. Okay, and there we go. The Fourier transform of the cosine with only one cosine at the third frequency is an output that has only that one output at the third frequency and at 32 minus, at n minus 3. How many samples are there? Oh, I set n equals 30. So we have one output at frequency number 3 and one output at frequency 30 minus 3. And that's calculated using the FFT and also using homework 6. We can check to make sure that that's enough to pass the grader. I ran 4 tests and I got 100%. So if I go to GitHub Desktop, then I should be able to upload that. Let's say homework 8, which is the DFT. I'll commit and then push it to origin. And then if I go to my GitHub, if I check that in 2024 fall, lecture 8, homework 8.py, as the W matrix as shown. Cosine of 2 pi k n over capital N minus j times the sine of 2 pi k n over capital N. Copy that URL, go to homework 8, and just enter in homework 8 the URL of your copy of homework 8.py, and I will go ahead and grade those before next week's lecture. Are there any questions about today's material? Questions in the chat or in the... All right, if there are no questions, let me go ahead and take the take attendance. Okay, everyone, please go ahead and register your attendance using this number. 皆さん、この番号を使って、attendance を、取ってください。お願いします。 それで31人になりましたけど、あと4人がいらっしゃいませんか？33人だったんですか？あと1人がいますか？あ、なった。OK, thank you everyone. みんな、お疲れ様でした。また来週、会いましょう。このビデオは、やっぱりこれからYouTube にアップロードしますから、また見たければ、お願いし、どうぞ見てください。はい、また来週会いましょう。